Hello and welcome to this design practice module 25. We were talking about the robust design approach, where we indicated that any engineering system can be really split up into signal factors, controllable factors, where control can depend either on the user or on the designer, depending on what is the level of control that is needed. And then there are noise factors, which are responsible for causing really the variation of the performance. And so, with the signal factor coupled with the noise factors as well as the control factors, engineering system would typically give a response, and the response might vary. And so, all these factors have to be tweaked in, where the only uncontrollable part is the noise, and somehow something needs to be done through design, so that that noise can be avoided completely, although is not it's seldom possible to do that. In real life situation, there are many causes for which variations might happen or creep in, which are beyond control. But at least the part which is in control of the designer or of the user should be made in a manner so that there is not much variation in the performance measures or performance characteristics. So, on one hand, one aspect is to rule out. So, how do you measure what is the performance variation? So, you have to actually again go back to the target value and then try to see how well deviated you are from the target, or are you within range. And then the Taguchi's approach says that the moment you are off target, you should start attributing a cost, so that you know exactly that you are off target and you are penalized for that, at least virtually, so that you can come back to the target again, and there are hardly any variations which are involved there. So, today I am going to take this up further and try to give you some understanding about the because I have already told you about the user defined control factors. We should also have a look, very broad look at the the designer defined control factors, and for that we will just start this lecture by looking into what are the factors which are controlled by the designer himself as regards the engineering design. So, if we really split it up into different categories, there are three different categories where we can actually attribute these controllable factors, where control depends more on the designers. One, of course, is the variability control factor. So, this is about the variability of the response, so the performance output, and you can say that if there is some kind of variability in response, it is the goal of the designer to somehow strategize in a manner so that such variability reduces, and there is overall an improvement in the performance being on target rather than off target. So, we will look at a very important example here, that which was actually proposed by Taguchi himself, about transistor gain in electrical power circuit, where we will talk on one hand about the response level of a transistor circuit based on the gain voltage, and on the other hand, because of the nonlinear characteristics of the target, you would find out that in two different voltage ranges for the gain voltage, there will be different output levels. One would be much varied in comparison to the other, and it may always be an appropriate idea to go at a higher level of voltage, output voltage, and put a resistance in series to that, so that there is a drop in voltage and the available voltage that is available comes down, okay, to the desired level for the system, and all you are ensuring is a control in the variability aspect by doing this job. So, so that example we are going to sort of see in details here about what really we mean by such variability control factors. We will also talk about target control factors. Target control factors are typically those which can be easily adjusted to achieve the desired functional relationship between the input signal and the response. Any engineering system, as you know, has a user signal which is being given by user control and also by a certain response output level. And so, if there is a variability in the response output level due to different causes, obviously the functional relationship between the signal and that response would change, because the user would typically want it to be to the desired level. And so, therefore, he has to do, for example, you think about the case of the steering wheel. If supposing the user finds out that he has turned the steering wheel by, let us say, 10 degrees, and the automotive takes a turn by very small amount, let us say 5 degrees, and the user has to do a little more of the steering turning, so that the automotive could take the desirable turn. Okay. So, the response level actually gives you a feedback, particularly when you are a user for a system, to somehow change your signal level, so that the response can happen according to your wishes. And so, this is about that target that you are achieving. So if there is a factor which actually helps you to achieve the target faster in between, that's called a target control factor. You can think about the gear ratio, for example, in such a steering mechanism of an automotive, and it can be selected during the product design stage itself, where you can get the required sensitivity so that the user is happy always. So if you're able to gauge if the user has a general habit of turning the steering x degrees, which will allow the automotive to turn y degrees, and he is in the comfort zone, saying that if he is turned x degrees, he finds the automotive to exactly turn according to his aspirations or needs, then you can say that it is the rightly defined gear ratio, and this can be one of the target control factors which a designer can put in place, so that with the input signal which is being generally given by the user, there is no variability to the response signal. Okay. So you can get the required sensitivity of turning radius to change in the steering angle in this particular basis. However, this can be controlled only once, because at the design stage, when you are actually planning the product, you have to be very careful about such factors. There is also a third different kind of factor, which is also otherwise known as a neutral factor. These are factors which will not affect either the mean response or the variability in the response, but still are existing. Why they are important is that there may be sometimes useful to know that they exist, so that modifications in those where the response or the input signal level response or the variability doesn't get affected can easily be taken off, so that there is cost saving. Okay. So you have to identify those factors which are essential and which exist, so that if the system is unaffected by their presence, although they are highly required by the system, okay, to support the system, so they may as well be gotten rid of, or sometimes may be corrected to a level where they are probably excessively designed, and you can get savings out of changing those levels, okay, to the normal values. So you can say that typically neutral factors are to be identified for cost saving aspects related to the overall design. Okay. So you can set them at their most economical levels, okay, so that such factors don't happen. So such factors don't affect the response of the target control. For example, in this case of let us say the gear ratio, and if it is a manual steering system, so obviously the amount of effort that you are doing on the steering wheel is going to get translated in terms of a gear ratio, in terms of the final turning radius of the 4-bar steering mechanism, so of an automobile. But if you are introducing something like a lubricant, okay, and the rate at which the lubricant is being infused into the system to perform, for satisfactory improvement or satisfactory performance of the system, is being controlled to a lower level while still being useful to, so there is no relation between the response level or the let us say the signal level, or let us say the variability aspect related to this automotive steering mechanism because of the oil. Okay. The oil always helps you to get some other desirable characteristics like necessary lifetime, for example, of the product, or maybe a little bit of more user comfort to some extent, because of the lubricating capacity. So unless we are jeopardizing that user comfort level, and we can still reduce the neutral factor to a level where oil usage is minimum, you may be able to do a better job with a lower cost. Although the presence of oil is very important, because that will give you some sense of lubricity while you trying to change directions in case of this automotive. So such factors are then known as neutral factors. So having said that, let us look into these two very important aspects, that how we can change the variability control factors and the target control factors in a real life problem. But before doing that, I would also like to emphasize a little more on a little more different kind of aspect, which is about the noise. Noise, which is an essential evil in all engineering systems, and somehow the question is, can noise also be classified into several different types, where there can be probably some strategies to remove the noise, or even like mediate the noise to a lower level. So if you look at the noise factors, the noise factors are generally responsible for the functional characteristics of a product. okay, deviating from the target value. And obviously when such a functionality deviation happens, it results in loss, a notional loss. And obviously if we looked at a large variety of these noise factors, we could categorize them into many different types based on what they're coming from. For example, there can be outer noise. Okay, so outer noise is typically due to the variables which are not really within the product but external to the product. Okay, but they do affect the performance of the product. For example, let's say if we talked about oil film for lubrication within a gearbox, typically would depend on the flow rate of the oil would typically depend on also other factors like temperature, humidity, and dust levels, which are otherwise not controllable. Okay, but based on this temperature levels, you may have a thinner version of the oil or a slightly thicker version of the oil, and you might have a different application aspect to the product which is being considered because of a factor which is probably there and is essentially an evil factor which has no other way to control. Okay, so the temperature in which you're operating your steering mechanism, for example, as laid out earlier, is not in your control. So, but still there is some noise because of the variability in the film thickness. Okay, related to the lubricity that is being provided by the oil in between. So, those are outer noise. Then there are also inner noise. Inner noise mostly come as a result of variations due to deterioration of parts and materials. For example, let's say when we talk about springs, with time there is a loss in resilience of springs, or maybe you can wear out parts due to essential component of friction. There may also be an increase in resistors, let's say with age and use of all the different resistances in circuitry, and with as a function of time, such parameters keep on changing and contributing to some uncontrollable factors which are present in the design, and you can treat them because the noise is resulting because of variation from within the component. A resistor, for example, in place and working for 24 hours for the next about 10 days may slightly vary in their resistance because of such long working hours, and because of the fact that it is a piece of such a kind of change in the resistance of the product with age could be considered to be an inner noise to the resistance itself or to the product itself. So, there is also a third different kind of noise which we commonly know as between product noise, which basically would mean that there is a lot of variation from unit to unit of manufacture what is happening in a process. Obviously, there is no control on only one aspect which will lead to such variation, no controlling of one aspect which will lead to such variation. There are many aspects associated with the manufacturing process. There are aspects related to materials, for example, which is going to come in. There is aspect related to the skill set of a person who is going to work in the particular, whatever contribution is making to the whole work system, which may vary, because of which such noise may come. So, there is going to be between the products from one material to the other, from one let's say batch to the other batch of the same product, for the same process and for the same material supply system, that a noise may generate. And so, this is inevitable, you can't help to prevent it. Material variation, for example, is one of the major cause of such a noise. If you could control it, it would have been very useful, but you can't help to control this between product noise which would keep coming. So, as the name suggests, the noise is a noise because it is uncontrollable. You can't give a definitive strategy to control such noise, and sometimes even controlling such noise may be a very, very expensive proposition, because you may have to think out of the box, change the whole process altogether, or sometimes create more or add or build more robustness by design, so that such noises may eliminate. For example, let's say look at the bolt example of a lower limit of, let's say, 11 kg force per millimeter square, which we considered in some of the earlier lectures for the selection criteria of a bolt. Okay, so if this level were to increase to let us say 15 or 20 kg force per millimeter square, of course, the overall cost would be higher in that case, but then because of the over development of the design, okay, or it definitely would add robustness, and so there may be a less possibility of overall variation because of between product noise, or let us say even like inner noise, so on and so forth. So, because you are over designing, and at the same time there is a cost aspect involved in over designing products, and so there really has to be a trade off, which has to be the basic theme for all designers, particularly in engineering design of products. So, when we talk about the Taguchi's approach to robust design of products and processes, we attempt to typically reduce the variability, and that is approached by changing the all the variability control factors through good design, maintaining required average performance, so it does not go outside the target range for the response of a system. There is of course a target set up for the response of such engineering systems, and this average performance can be through appropriate adjustments in the target control factors, so on and so forth, and that basically gives you an idea of how robust design can be carried out. So, let us look a little more details now, as I talked earlier about what is so different about variability control factor and target control factor, and in this case I would look at an example given by Taguchi itself about a transistor gain. So, let us say when we talk about an electrical power circuit design, the quality characteristics that may be of interest to the production personnel is, in one case it could be something related to the output voltage of the product. Let us call the output voltage Y as in this particular case, and there may be a target value for this output voltage, and this is what we are referring to is the transistor output voltage, okay, and the target value of Y0 is set in for output voltage of particularly Y, and Y could be away from Y0, as you know, because of process variabilities. So, they are always deviated, and typically when we look at the transistor setup and the circuit, this output voltage of the transistor is also very inherently connected to something called the gain of the transistor. So, gain is sort of a factor which is an amplification factor used for multiplying the input response, so that the output response can be multiple folds. And so, typically in this case let us consider the gain of the transistor circuit to be about x, okay, whose nominal value can be controlled, and because of such control, as you will see that the response of the transistor is such that it is highly nonlinear, in fact, that it results into a situation where by intelligent designing we can reduce the variability somehow in the output voltage Y. Okay. So, obviously, when we look at x, which is the gain, the product design engineer can select the nominal value of x to be about x0, which is the target gain factor of the circuit, and to achieve the target value of y0, this is sufficient. Okay. So, at gain x0 you can say that the transistor circuit should ideally give an output voltage of y0. However, as you know, in real life situations, the transistor gain can deviate quite a bit from the nominal value x0. So, there would be a range of values, let us say x, across which this deviates from gain x0 to any other x which is greater or lesser than x0, and these are typically because of many reasons, like let us say variation in manufacturing, there may be imperfections or defects, particularly in the purity of the silicon crystals which have been used to make transistors, or even some other polymers which are used sometimes to make transistors. You can also have deterioration during the circuit's lifespan, change of resistance elements related to the interconnects which may lead to such response variation. You may also have some variations related to temperatures at which these circuits are operated. Not every transistor circuit is set upon to operate at a constant temperature. So, there is going to be selective, there is going to be a certain amount of deviation definitively on the gain value x, and because of that there is also going to be a change in the output voltage, and so there is a question of variability which comes. So, how much away from y0 is y, at what level of gain x from x0, which is the target level. So, let us look at this, that in fact, if we select the or if you look at the nonlinear response of the output voltage y versus the x, as you can see here, one can recall that, let us say if the gain value were at x 0 earlier, that means the gain is set up at x 0 and there is certain variation here in x 0. This variation is with x 0 centered as the mean value. So, obviously at x 0, as you know, as we have discussed earlier, there is going to be a output voltage y 0, but because the x 0 is varying between, let us say, some level x 0 minus 2x 0 plus, okay, there is going to be some variation in the output voltage also. Let us call it y 0 plus and y 0 minus, okay, and you are seeing that the range of variation here is quite high, but because the resistance or the output is actually a nonlinear function of the gain at a higher gain voltage. Let us say if we operate at x 1, where the variability here is accommodated more, okay. So, you can really go up to a greater amount of x 1 plus I am sorry, x 1 minus and x 1 plus range, excuse me. So, x 1 plus minus x 1 minus, as you know, is definitely much greater than x 0 plus minus x 0 minus. So, you are accommodating a higher amount of gain range, but the overall effective variation here between y 1 plus and y 1 minus let us say is much lesser, okay. So, y 1 plus minus y 1 minus, which are the two extremities with mean round y 1, is much lesser in comparison to y 0 plus minus y 0 minus, okay. Yeah, I am sorry, the sign needs to change, much lesser here. So, but then the question that comes out here is that y 1 obviously is a much higher voltage, which is away from the target y 0. It should have been operating at a output voltage of y 0, but now it is y 1. So, obviously you have to add a resistance in circuit. So, let us suppose that if supposing the resistance is R 1 at the series level, the voltage is somewhere around y 1 and it can reduce to y 0 if you could change or increase the resistance from R 1 to R 0. So, you add certain resistance component to the output voltage, so that because of the drop, the y 1 changes to the target value y 0. So, in this case, the the target control factor is the resistance, okay. So, the resistance is actually allowing the output voltage to change back to the target value. So, you can call this to be a target control factor, okay, target control factor, and the variability control factor is the transistor gain, okay. So, you are seeing that for a larger amount of gain, you are getting a smaller amount of output range of the voltage, okay. So, variability control factor is transistor gain. So, this is a very appropriate example to understand what person means by target control factor and a variability control factor as far as engineering systems are concerned or engineering system design is concerned. So, I would like to probably migrate to a new topic about carrying out strategies or processes in industry with respect to the implementation of the concrete engineering, as well as giving you a methodology to understand where a deviation is coming and what are the reasons for such deviation to happen. And there is a technique, a very useful technique called failure mode effect analysis, which is used in most of the industries for looking at some engineering design performances and recording as to what would be the appropriate causes of variation. So, in the next module, when I start next week, I would like to probably go ahead and give an introductory session on this FMEA and try to do it from a process point of view, that if there is an existing process, how FMEA can be done to improve the process, where we are essentially again improving the variability as a as an approach to the robust design at the behest of controlling some important factors and not a whole lot of factors. And FMEA kind of gives you a roadmap of prioritization as to what needs to be addressed more priorly in comparison to the other factors, so that the overall variability can reduce effectively. So, with this I would like to end the lecture module here, and we will do FMEA in the next lecture. Thank you very much.